Hello. In this session, we're going to talk about governing equation for 3D heat conduction. Um, so let's assume we have a 3D element that the dimensions are dx, dy, and dz. So let's create a 3D conduction element. So let's assume this is my x direction, vertical is my y direction. So this is my y, and this is my z direction. In terms of dimension, this is my dx, along the y is my dy, and along the z is my dz dimensions of my finite element. Now, let me show you in another color the heat into the element and heat leaving the element. Similar that we can do for 1D heat conduction. For 3D, we can say Qx comes along the x at the dz dy area, which I'm showing it with this. So as you can see, this is where Qx comes in and leaves on the other side of the element. And when it leaves, we call it Qx plus dx. And the reason is if the first part of the Qx was entered at location x, lowercase x, and the dimension of my finite volume is dx, so the other side would be x plus dx. That's the location that Q sub out, leaving out. That's why we call it Qx plus dx, because that's the location the Q is leaving. Same thing for y. Y comes in at the bottom of the final element, leaves on top. Again, when it leaves at y plus dy, because dy is the thickness of my final volume and y was initial location. I'm showing it here. So at the outlet of Q along the y direction, the location is y plus dy. So that's how I call it. Z, same way, comes in at Q sub z, let's assume, and then leaves at Qz plus dz, because dz is the thickness of my element along the z direction. We are going to also consider internal heat generation. I can show it here inside our elements. So let's show it with Q dot generation as well. And with that, we are ready to write our energy equation. So let's go ahead and write it down. So we can say, in simple analogy, total energy coming into my control volume plus the rate of energy generated inside my control volume should be equal to the portion of energy leaving my control volume, and remaining is the portion that is stored in my control volume. So in other words, I can say E dot in plus E dot generated should be equal to the portion leaving E dot out plus the portion is stored, the change, the internal energy of my control volume. So if I split down the energy in, simply I have Q dot at the X, Q dot at the Y, and Q dot at the Z direction. So these three are my E dot in that I'm showing it here. And we show generated energy rate as Q dot gen. That takes care of the second term in my first equation. This should be equal to, I'll write it down, the remaining energy out, as we discussed, Q dot x plus dx leaves on the x direction, Q dot y plus dy leaves along the y direction, and Q dot z plus dz leaves along the z direction. And the portion which is stored inside the control volume, we can show it as variation of the energy over time, and we show it as dE over d tau. That takes care of the changes in internal energy of the volume, which we also show it as amount of energy, the rate of energy stored in the control volume. Now let's go ahead, break down each equation. So let me show this like this, and try to simplify this governing equation. First, I'm going to show the Q dot x. For Q dot x, I can simply say I can use the Fourier's law, which is minus k times area times variation of temperature along the x, dt over dx. So I left the area blank, but let's see what is my area in this case. What is the area that Qx is crossing? That's the question. So Qx comes in, and the area that Qx crossing is nothing but dz times dy. So this is the area that I'm showing it right now. So as you can see, this area is nothing but dz over dy. Why? Because one dimension of this horizontal length is dz, the vertical height is dy, because that's along the y direction. So that area is dz over dy simply. So here I put dz dy instead of area. And now I have my q dot x. And similarly, I'm going to write down q dot x plus dx. That's the heat, rate of heat leaving the control volume along the x direction, which we're going to use the series Taylor series expansion and rewriting the same Fourier's law, but instead of dt over dx, we're going to use it at the location of x plus dx. The final form is this minus k del t over del x plus del over del x of k del t over del x times dx, and you have to multiply this by area, same area that we use for inlet as well. So again, we use Taylor series expansion to go from minus k dz over dy dt over dx at x plus dx. When you simplify this, this is what you get. We showed it for a 1D conduction, so we're skipping the details of how we apply the Taylor series here, but this is what you get for a final form. Now, we have to do the same thing for q dot y and y plus dy for the outlet, and same thing with z direction. So let's go ahead, do q dot y quickly. Simply Fourier's law, which is minus k times the area that I'm going to skip for now, leave it blank, variation of temperature along the y. What is my area that q dot y is crossing? This is q dot y. And going off bar along the y direction. My area that q dot y is crossing is this. And what is this area? Simply dx times dz. dx times dz gives me the full area that q dot y crossing. So dx times dz is my area. And same analogy for outlet. Add y plus dy. I get minus minus bracket k del t del y plus del y of k del t over del y dy times same area, which is dx over dz. I'm going to do the same thing for q dot z. Fourier's law minus k. Now we know by experience that the surface area that q dot z crosses is dx dy del t over del z. And same thing for outlet portion of this, minus k del t over del z plus del over del z k del t over del z times dz dx dy. So far I have my E dot in and E dot out terms written. So I have Q dot X, Q dot Y, Q dot Z, and on the other side of the equation, I have Q dot X plus dx, Q dot Y plus dy, and Q dot Y Z plus dz. Now in this section, let's talk about Q dot generated. So internal energy generated within the finite volume we have. So Q dot generated, we can usually show it as a volumetric heat generation rate, which is Q dot times the volume. What is the volume of our finite volume? Is simply dx times dy times dz. If you multiply the three dimensions of our cube, you get the volume of them. So, and by the way, remember the unit for Q dot is watt per meter cube, right? That's the unit for Q dot. That's why I need to multiply that by volume with the unit of meter cube. So we can cancel out this meter cube. So dx, dy, dz are simply meter, 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 so meter cube. So these will cancel out meter cube. So at the end, I have the unit of Q dot gen as watt, which is the consistent unit with other terms in the same equation. So that's what I have in terms of Q dot gen. One last term I need to work on is dE over d tau, which is stored energy in the finite volume we have, as well as you can also call it variation of internal energy inside the control volume over time. So let's look at that. My last term is nothing but variation of energy dE over time, or d tau. And we know that we can show it as rho C. Rho is density, C is the specific heat capacity times the volume. Now volume we just showed dx, dy, dz, and multiplied by variation of temperature over time, theta over del T over delta. We talked about it when we derived the 1D equation for conduction. Then on the side note, I can quickly talk about it here as well. Side note for this. Remember, we can show the rate of energy as m dot Cp delta T, or sometimes we show it as mc delta T over delta time. This is exactly the same. Here, mass is nothing but density times volume, which in this case is rho times dx, dy, dz. Now, this delta or time term, if it comes under temperature, this is the equation we have. Or sometimes if you have a variable mass, we can bring it under density times volume, so you get m dot. Bottom line, this is kind of another form of the same equation, that by knowing the density, a specific heat capacity, volume, variation of temperature over time, we can um, have this. And by the way, let's quickly see what is the unit of density. Unit of density is kilogram per meter cubed, right? That's the unit of density. What is the unit of C? I mean, I can show it here. Density is joule per kilogram Kelvin. What is the unit of dx, dy, dz altogether? And we know dx times dy times dz gives us a volume, which so the unit is meter cube, right? What is the unit of del T over del tau? T is temperature, so Kelvin, and tau is time, so let's say second. So if we try to cancel out and simplify this, I can say meter cube with this meter cube cancel out each other. Kilogram and this kilogram cancel out each other. Kelvin and Kelvin cancel out each other. What I have at the end is joule over second. What is another name for joule over second? It's watt. And that's exactly consistent with other terms. So all, as you saw here, all of those terms has the same unit of watt. That's why we can add them together in this equation. So far, we have all terms of this governing equation written down. Now let's go ahead and substitute all these simplified terms that we just developed, put it back. So substitute in the main equation here and try to simplify it so we can get a one overall simplified version for our governing equation for 3D conduction, right? If I go back and remember, similar to 1D conduction, you can cancel out few terms from right hand side of equation with the left hand side of the equation and kind of simplify your process. But let's go ahead, work on this together. So simply I can say q dot x is nothing but minus k dy dz times del t over del x plus q dot y, which is nothing but minus k, so let me erase this plus, minus k dx dz del t over del y plus, let me see if I can, plus dz. I'm gonna erase this part so I have some room here. Dz is minus k dx dy del t over del z. And then I had one more generated heat generation term, which was q dot dx dy dz equal to, on the other side, I had qx plus dx, which was minus k del t over del x plus del over del x k del t over del x times dx times dy dz. Same thing for y term, k del t over del y plus del over del y, k del t over del y dy times dx dz minus k del t over del z plus del over del z k del t over del z dz dx dy my volume, my area, and one last term was energy stored, which we showed it to be rho c specific heat dx dy dz time variation of temperature along the time, which is dt over d tau here. So this is all terms together. We are sure that we can simplify a good version of this. Let's see how we can do this. First of all, you can tell, we can drop this term, minus k dy dz del t over del x, with the first term here, minus k del t over del x multiplied by this dy over dz, right? So I can drop this term here together. Can you see this? Same thing along the y direction. I can drop this term by the first portion of this. Again, let me show it one more time. I have minus k dx times dz del t over del y, and on the other side of the equation, I have minus k del t over del y, which at the end they're multiplied by dx over dz. So this term is exactly similar to the other term on the other side of the equation. They can cancel out. Same thing with z and with z direction. Another thing we can cancel out is that let's see, areas are, yep, another thing we can cancel out is the volume. Look at here. Let me get another color. Is that, so first three terms are gone. I have dx dy dz as a volume here. On the other side of the equation, I have it here. I have dy dx dz here. Another volume here. Another volume here. How about we cancel all of those because they are shown on the other side of the equation. Another way to put it is that let's divide all the equations by dx dy dz, so this way they cancel out each other. Okay, now with what we have, let's go simplify our equation and kind of write it in the final form. So I start here. What I'm gonna do, I'm gonna uh, bring these terms with the negative sign to the left-hand side of the equation, so they become positive as they move to the other side of the equation. For example, in this case, I will have minus del over del x. Actually, with minus, I'm going to the other side becomes positive. So del over del x of k del t over del x plus, same thing for y direction, del over del y, k del t over del y. We don't have that volume, we don't have anything else. Same thing with z. And we're going to keep this positive on the same right-hand side equation. And we also have a heat generation term. We're going to keep it over there. So this is going to be our final form. Let's see what we get. So I will have del over del x, k del t over del x, plus del over del y, k del t over del y, plus del over del z, k del t over del z. I'm going to keep the heat generation parametric coefficient there, and I'm going to keep an equal sign, keep the rho c del t over delta on the same side, right hand side. So I have density, specific heat capacity, variation of temperature by time, rho c del t delta. So this is one final form that we have for 3D conduction. So let's put this in a kind of nice block showing that this is my final form. Here, as you notice, k is within the parenthesis under del over del x, same thing under del over del y and del over del z. Now, in some cases, if the temperature variation is large, you can assume k is a variable. So we're going to keep it in this form, but in many problems, you can assume K remains constant. So thermal conductivity of the material doesn't change significantly in some cases along the X, along the Y, along the Z direction. If that's the case, we can even simplify this governing equation furthermore. So let's say for constant thermal conductivity, K, if K can be assumed constant, what we can do is that if it's constant, it comes out of this derivative. Same thing with along the y and z. So you can factoriate it. And as you will see, I'm going to divide all equation by k. So somehow we show it in another form. So if k can be constant, we will have our equation as second derivative of t with respect to x, second derivative of t with respect to y, second derivative of t with respect to z because k is out. And then we divide all sides of the equation with k. So this q dot gets divided by k. And I have 1 over alpha thermal diffusivity del T over delta. So this is going to be my new final form if K can be assumed constant, and you will see that I have rho times C, and I need to divide it by K, but I showed it as 1 over alpha. I'll talk about it in a second. So thermal diffusivity is, we already defined this, but thermal diffusivity is alpha, which is nothing but K over rho C, right? So this is called thermal diffusivity. Let's write the units, so make sure we understand everything. What is the unit of thermal conductivity? Everyone should know this. This is watt per meter Kelvin. What is the unit of density? Kilogram per meter cube. What is the unit of C, specific heat capacity? Joule per kilogram Kelvin, right? So that's what makes thermal diffusivity, K over rho C. Let's simplify this. I have kilogram and kilogram cancel out each other. I have Kelvin in denominator here and Kelvin in denominator on top. They can cancel out each other. I can write joule watt as joule per second, right? That's another name for watt. So I can cancel out joule and joule here. Well, I also have 1 meter, which I can cancel out with 1 meter over here. So I have meter cube here. So at the end, I end up with meter cube, which is the denominator of the denominator, so goes all the way on top. And then I have 1 over second as well, so so I can show my unit for thermal diffusivity as meter square per second. And as you saw, then instead of showing rho C divided by K, which is the 1 over alpha, I'm simply showing 1 over thermal diffusivity coefficient. So this is what we have for 3D conduction. So far we talked about 3D conduction heat transfer in Cartesian coordinate system, where X, Y, and Z are our coordinate system. Now, in some cases, it's easier to model our problem in cylindrical coordinate system or a spherical coordinate system. Imagine water is flowing inside the pipe. Water and surface temperature of the pipe has different temperature. So there's a heat transfer happening between the surface and the water liquid flowing inside the pipe. So to understand that, you need to solve the governing equation for heat. And then through the thickness of the wall, let's say, of the tube. And for that, it's much easier to use the cylindrical coordinate system. Same as story with the spherical geometry. It's easier to use the spherical coordinate system. So in the next section, I'm going to show the conduction equation for cylindrical coordinate system and a spherical coordinate system. Well, in cylindrical coordinate system, same procedure will be applied. We're going to skip that because we already defined those for Cartesian coordinate system. But before I write the final form of the governing equation in cylindrical, let's discuss the cylindrical coordinate system itself. So let's assume we have a cylindrical geometry like this. This is my center line. So along the R, you have one dimension, so you can call it R. So you can make your cylinder at any radius you want. So R is a variable like X. R is a dimension that in cylindrical coordinate system lets you define what radius of geometry you have. You also have the height, dz, kind of showing you this is your base of your coordinate system, kind of showing you what's the height of your control volume is in cylindrical coordinate system. And also you have an angle. So starting from, so this is the angle phi starting from a base, kind of shows you if you want to spot any point in the coordinate system, in cylindrical coordinate system, you should be able to show it with a certain r, certain z, and certain angle. So instead of x, y, z, we are showing it with r, z, phi. So in the final form of cylindrical coordinate system, you will have 1 over r del over del r k r del t over del r plus 1 over r squared del over del phi, the angle term, k del t over del phi plus del over del z, k del t over del z plus q dot, which is our volumetric heat generation coefficient, is equal to rho c del t over del ta. Let me put a box around this. This is our final form for governing equation of heat in a cylindrical coordinate system. Remember here we had r, z, and phi as our variables. In the Cartesian coordinate system, we had x, y, and z. Remember in the previous one? Now we have in the form of r, z, and phi, and you'll see that del t over del r, del t over del phi, del t over del z. So r, phi, and z are our variables here. This is our governing equation. We can use here for the cylindrical coordinate system. One more thing I want to highlight is that this might help us better as well, that if this is R and this is Z or DZ in this case, and this is showing my phi, the angle for my base, this is just can be a slice or control volume that we can apply all our incoming and leaving energy and heat generation and changing internal energy of our finite volume in this form for such a system. Again, R, phi, and Z, and those are our variables for cylindrical coordinate system. Now with that, let's move on and do the same thing for a spherical coordinate system. By the way, we'll do examples of different coordinate systems, so we definitely discuss those in further details later. So in a spherical coordinate system, we can say, you can assume any spheres that instead of x, y, and z, so let's assume typically in Cartesian coordinate system we have x, y, and z, right? In a spherical, we can show it with, again, with a radius r. So any sphere has a radius. So by changing the radius, you can generate different sizes of a sphere, and you can pinpoint any point inside that sphere with the r with an angle in one direction and another angle compared to z. So theta. So r, theta, and phi are your three variables in the spherical coordinate system. Remember, in this cylindrical, we had r, height, z, and phi. But here, in a spherical, we have two angles and one kind of dimension in terms of radius. So in a spherical coordinate system, we can show our governing equation would be 1 over r del 2 over del r squared rt plus 1 over r squared sine of theta del over del theta sine theta del t over del theta plus 1 over r squared sine 2 theta del 2t del phi squared plus my heat generation term is equal to 1 over alpha del t over del tau. This is my final form for a spherical system. That I show it here. So far we had 3D conduction heat equation for Cartesian coordinate system, for cylindrical, and for spherical coordinate systems. In the next step, let's try to understand each term and let's practice simplifying the governing equation depending on the specifics of any problems. So in this case, I'm gonna scroll down and rewrite our governing equation quickly. So governing equation which I have del 2t del x2 plus del 2t del y2 plus del 2t del z2. Remember that was for constant thermal conductivity, Cartesian coordinate system. 1 over alpha del t over del tau, as you remember. And so this is our governing equation. We work together to draw this, right? Let's assume we have a steady state problem, which is a one-dimensional with no heat generation, with no heat generation. Okay, so with no heat generation. So let's look at that. Whenever we have a steady state, we can simply say variation of temperature over time is 0. So whenever it's transient, we talked about it, that We are assuming boundary conditions change over time. In a steady state problem, boundary condition does not change over time. So del t over del time is 0. So we drop this term because it's a steady state process. So boundary conditions remains constant regardless of time. Here it says no heat generation. So simply the heat generation term goes to 0, or we're assuming Q dot equal to 0 because there's no heat generation inside that particular problem. And it's a 1D problem, one dimensional. So you can keep one dimension, drop the other two dimensions. So let's assume we're going to keep the x direction and let's drop the y and z. So your final equation in this case would be what? Would be second derivative of temperature with respect to x equal to 0. So you just keep this term. Everything else is 0. This is your equation. Now to solve this particular problem, you need to solve this. Let's look at another problem. We have a steady state, one-dimensional heat conduction, heat flow with the heat source. Let's solve this together. So in this case, you have a steady state 1D flow with heat source. So let's go back to the overall equation we had initially, and let me erase those so I don't repeat writing those. So first of all, we said it's a steady state. That means transient term drops, right? And then 1D, so I'm going to drop the y and z terms. And with heat source this time, so we're going to keep the q dot k and we're going to keep the one dimension here. So my total equation, my final equation is this term plus this term equal to 0. So all I have is del 2t del x2 plus my heat source term equal to 0. That's my kind of final equation in this case. Let's look at another scenario that I have two-dimensional steady state heat conduction without heat flow or without heat source. So in this case, it's a 2D conduction, a steady state, and no heat generation inside. Let's look at this scenario quickly. So in this case, it's a 2D, so I'm going to keep x and y. Again, this is optional. I mean, you can keep x and z or y and z, doesn't matter at all. So let's drop the third one in this case, z. I'm going to drop the z. Still, it's a steady state, so it's not transient. So I'm going to drop the transient term still, but keep this at my heat generation term as well. Oh, sorry, it says without heat source. So if that's the case, Q dot is equal to 0. So this term drops as well. All I have is the first two terms here, really. So my equation becomes del 2t del x2 plus del 2t del y2 equal to 0. That's my governing equation that I need to solve. This is all we have for 3D heat flow conduction in Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate systems. Now we can simplify our governing equation, drop those terms not needed in particular cases. If it's transient, we keep this. If it's not, we drop it. And same analogy for other terms. And we simplify our governing equation. We will see that in next topics, we will use this governing equation to solve for a particular problem. With that, I stop this session and we see you next. Thank you.